In this video, I'll introduce the acceptance-rejection method, or AR for short. And the idea of the method is that in order to simulate from f of x, the distribution we're actually interested in, we instead simulate from g of x another distribution, and then we reject in a clever way what we don't need. What I mean by that is that if we imagine that f of x is looking something like this. This is the distribution we want to simulate from, but we can't, or it's slow, some of the other methods. Then instead we'll take another distribution, g of x here, and it actually has to be multiplied by a constant c, but for now we'll just forget that. In this case, the distribution I'm simulating from is clearly the uniform distribution. It's flat. That's usually not the optimal case, but for now we'll just accept it as is. What we'll then do is that we'll realize that we need to adjust when simulating from this uniform distribution a bit. Specifically over here, we'll have to throw away a lot of our samples so that fewer of them survive, because f of x has tendency to generate fewer samples here. But over here we won't have to throw away quite as many samples, so we might say that if we just color in all of this, then over here we want to reject often, so we want to take a lot of the samples we generate from g of x and throw them away, while here we will want to reject only a few samples. And specifically, terminology wise, this is called the envelope. Okay, and it'll then later on, and we'll prove this, it'll turn out that we should accept, that is, we should not reject with probability f of x over c times g of x, the envelope. Now, the way this method works, and I hope this has given you sort of a very vague idea at least, is that first we'll draw x from let's call it capital G, the proposal distribution, and then we'll draw u from the uniform distribution. And we talked about previously how we could simulate from the uniform distribution, and we might imagine that we can simulate from G using inversion, which we already covered. And then in the last step, having drawn x and u, we'll say if u is less than equal to f of x over c times g of x, set y equal to x, else go to step 1. And we might say that this means that we will accept x. Okay. What is required of this method is that one, we should be able to that we can simulate from g of x, well, from g, from the proposal distribution. Actually, I might want to add that. We'll just call it the proposal distribution. So we need to be able to simulate from g of x, and it needs to be the case that f of x is always less than or equal to the envelope, that's c times g of x. And this then implies that the support of g of x includes support of f of x. So g of x must at least have the possibility of drawing any random variable, any random value, which could also be generated by the distribution we're looking for. And I just want to highlight some notes for comparing this method to inversion. And the first thing is that we avoid the inverse of the distribution. That's the generalized quantile function, or the quantile function, which we noted previously was often very slow to be evaluated. So if that's the case, that you're simulating from something where inverting the distribution function is slow, then you might want to consider acceptance-rejection. And secondary is that g of x should be similar to f of x to accept often. And what do I mean by that? Well, if we turn back to our sort of intuitive example over here, well, over here g of x is very far from f of x, and we had to reject a lot of the samples generated over here. But if g of x and f of x is very close to each other, then the space, the red space here you can call it, where we reject is minimized. So when we look at the algorithm we just introduced, then we'll note that the speed of it, the speed with which we can generate our random variables, will depend on three things. And first, of course, is that simulate from g of x is fast. Simulating from g of x is fast. The second, of course, is evaluating f of x over the envelope is quick, because we need to do this at every step. And lastly, we need to be able to accept often, because otherwise, even if we're simulating really quickly and we're evaluating whether we should keep the sample really quickly, if we have to throw away most of them, then it's still going to be slow. But if these three criteria are met, then we should have a very quick method of generating random variables from our desired distribution. Now I'll just prove what we actually already noted on the first slide, the first paper, the probability of accepting. And specifically what I mean by that is the probability of u less than or equal to f of x over the envelope. This is our definition of when we would accept a sample, and we'll just take the expectation of this conditional on x, so conditional on the sample which was generated. Hold on, I actually need another bracket close like that. And well, because of the properties of the uniform distribution, specifically the standard uniform distribution, specifically that the probability of u being less than or equal to some number a is equal to a for a between 0 and 1 for the standard uniform distribution. So this simplifies a little bit, and it becomes the expectation of f of x over the envelope and then we'll just use the definition of what the expectation is. That's going to be the integral of f of x over the envelope, and that's going to be when we're sampling from g of x with respect to dx. Now here we're varying according to x, so we can take the c out, so we can write this as 1 over c times the integral of f of x over g of x multiplied by g of x dx. But then of course might notice that the g's, the g's will cancel out, and we'll have 1 over c times the integral of f of x dx. And with a clever little trick, we might recognize that the integral of the density is always going to be 1. It's just a probability measure. And then what we're left with is 1 over c. So we have the probability of accepting is 1 over c. And well, what can we use that for? Well, let's see, we'll take the green one here. This then implies that we want small c to accept often, right? Okay, so that was a very useful proof or insight from the proof. And then the second proof I'll use here is that sort of the proof that the method actually works, and that is that we'll have the probability of capital Y, so that's an accepted sample, the probability that belongs to some set A is going to be equal to the probability that X, the sample generated, belongs to A, conditional on us accepting it, U being less than or equal to f of x over the envelope, right? And this is a conditional probability, so we'll just use the definition of this. So we'll have the probability of x belonging to A along with u being less than or equal to f of x over the envelope divided by what we're conditioning on. That's then the probability of u being less than or equal to f of x over the envelope. But then we might notice that hold on, that this thing we already know is 1 over c, because we just proved that. That's the probability of accepting. So we have that all of this becomes c times integral over the area A g of x times f of x over c times g of x with respect to d of x. And then again we might note that the g's cancel out, and we might also note that the c's cancel out. So then we're left with the integral over A of f of x dx, and then that's exactly what we're looking for. The probability of y belonging to some outcome A is the integral of the probability of the target distribution, what we're looking for. Okay, and now we'll look at a small code example. In this example, I'll just be simulating from this density function here using acceptance-rejection. So I'll start by clearing the memory in the screen. Then I'll define this anonymous or local function. I'll set two parameters, alpha and beta, which I'm going to use in the PDF from the F distribution, which will be our proposal. I'll mark this, and like before I'll press F9. We'll also need our C constant, which will just set to 3. It's not terribly important at this point. Then we'll create x, which will be a number line going from 0 to 4 with increments of 0.001. So if I just mark it and press F9, we can see what's stored in the variable here. It's about 4,000 values in it. Then we'll evaluate the target density. That's the anonymous function we defined up here. We'll call x to it and put it in y1. We'll call our proposal, and we'll call our envelope to put in y3. We'll also grab the probability of acceptance by dividing the target density with the envelope. And then we'll plot them so we can have a look at what that looks like. I just need to dock it here. Okay, and we can see here the target density is the blue line, it's this distribution like this. The proposal density is the red line. You can see it's actually below the blue line in some places, and that's why we need our C to scale it up. That gives the yellow line the envelope, C times G. We can also look at the probability of accepting. So if, for example, we have realization around 2, we're going to have around 0.2 or 20% probability of keeping it, of accepting. And it's going to be lower in the extremes towards the greater values, and it's going to be greatest around here. It looks like around 1, or maybe actually here in the very small values. Okay, so now let's do the acceptance rejection algorithm. First we'll set, okay, we want 20,000 values, so I'll mark that and press F9. We'll start I'll just talk the code through first. So we'll start a counter we'll call J, which will be for the attempts or the tries to simulate a random variable. Let's see here. Actually, this is not terribly important, but here's where the main of the code is. We'll start another counter, which we'll call I. Then we'll do a while loop, and we'll say as long as I is less than n, which was our 20,000, then we'll keep doing what's in here. So this piece of the code will keep going until I reaches 20,001. So first we'll draw our proposal x, then we'll draw our uniform u, then we'll do the acceptance rejection step. If u is less than or equal to the target density divided by c times proposal, then we'll set I to be equal to the x value, and we'll iterate up I by 1, and then we'll continue. But no matter what, we'll keep increasing our j value at each attempt, whether successful or not. Okay, so I'll just mark this part of the code, starting with the tick, which starts the Matlab clock, and ending with tock, which stops it. Then while that's running, this part here of the code, you can just ignore it. It's just something I used to plot something else we won't look at. This part up here. Anyway, the code ran for 4.6 seconds. It seems okay to get 20,000 random variants. We have an acceptance frequency, that's n divided by j, of 33%. That seems excellent, since we had a C of 3 and 1 divided by 3 is 0.333. Repeating. So let's plot a histogram with the target density here. So we see the histogram, it nicely lines up with the target density. So that seems to indicate that our simulation was successful and we were able to simulate from this distribution which we had put into our target density up here.